Hello everyone. This is a lecture on chapter 1.8, which is on inverse functions. So we will describe here, we will explain what inverse functions are, and then we will talk about how to verify inverse functions, uh, create an inverse function, and then identify domains. So here are the topics that we are going to cover. We will first have to verify if a function will have an inverse function or not. Not all functions will have an inverse function. So we will study how to verify inverse functions. And then once we verify, we know that a function will have an inverse function, then we will learn how to find the inverse of a function. So there is a step-by-step process, and we will go through that process to create an inverse function of a given function. Then we'll use the horizontal line test to determine if a function has an inverse function. These are some different ways of identifying whether a function has an inverse function, and then use the graph of a one-to-one function to graph its inverse function. So graphing inverse functions is what this topic is about, and find the inverse of a function and graph both functions, the original function as well as its inverse, on the same axis. Let's go through the definition of an inverse function. All right. So what does inverse of a function mean? It says here, and I'm going to read through this first and then try to explain. All right. Because when I read through it, it may not sink in immediately, but once we go through some examples, it might make things more clear. So it says, let f and g be two functions such that f of g of x. So here we are talking about a composition, a composite function. Remember, we are, as you can see in the notation, we are inputting one function into another function. So f of g of x equals x, and for every x in the domain of g. And then g of f of x equals x for every x in the domain of f. So what essentially they are saying is, if we plug in the g of x function into f of x, the resulting function will be equal to x. And conversely, if we plug in f of x into g of x, then the resulting function will be x. Now, if that happens, that means these two functions, f of x and g of x, are inverses of each other. Once we go through an example, again, it'll become more clear. All right. It says here the function g is the inverse of the function f and is denoted f to the power, well, it's f, it reads like f to the power minus 1, but it's actually f inverse. This is not really an exponent, all right, so to speak. We represent, we denote f inverse as f with a superscript of -1. So what they are saying is over here, thus f of inverse of f of x equals x, and if we plug in the f of x function into its inverse function, we get an output of x. The domain of f is equal to the range of whatever the inverse function is, and vice versa. In other words, what they're saying here is the domain of the original function. So let's say there is a function f of x and f inverse and its inverse function. So what happens is we have a domain and range for each of these, for f of x. What happens is under domain and range, for the inverse function. So the domain of the original function becomes the range of the inverse function. All right, the domain of the original function f of x becomes the range of the inverse function, and the range of the original function becomes the domain of the inverse function. All right, so the domain and the range switches between the original function and the inverse function. Now here is an example verifying the definition of an inverse function based on what we learned in the previous slide. All right, so what we were told in the definition of inverse functions is that if we plug in one function, so there's f of x and g of x, let's say. So if we plug in g of x, if we create a composite function by plugging in g of x into f of x, the output value should be x. And likewise, if we take f of x and plug it into g of x function, the output should also be x. So whenever that happens, that means f of x and g of x are inverses of each other. So that's what the definition told us. Now let's go through an example problem to see whether that happens or not, whether we get an output value of x or not. So they've given us two functions. F of x is 4x minus 7 and g of x is x plus 7 divided by 4. So what we have to do first is we have to evaluate the composition of g of x, or rather f of g of x. All right, so we are working through a composite function here. We are taking g of x, plugging it into the f of x function. All right, that means whatever g of x is, we have to plug it into x in 4x minus 7. So here we go, f of x plus 7 divided by 4. So you see, we have 4 here in the f of x function. 4 times, they've replaced x next to the 4 with x plus 7 divided by 4, and then there's minus 7. So we get x plus 7 minus 7 equals x. So I'm going to again work this out so you can see how we get x plus 7 minus 7 equals x. So I think this much you understand, that where they have plugged in g of x into x in the f of x function. So let me work this out and see how they got to x. So we have 4 times x plus 7 divided by 4 minus 7, correct? Minus 7. So 4 and 4 divide. 4 and 4 divide. So what are we left with? X plus 7. X plus 7 minus 7. And plus 7 minus 7 is 0. All right, these two, plus 7 minus 7 amounts to 0. So we are left with x. So this is how they got x plus 7 minus 7 by dividing 4. As for the next one, so we got an x. Now we have to see whether the converse of that also gives us x. So that means if we plug in f of x into the g of x function, if we plug in f of x into the g of x function, we should also get an x as the resulting function. All right, so now into g of x function, which is this, we plug in 4x minus 7. So there is an x in the g of x, so we will be plugging in, we will be replacing this x with 4x minus 7, and that's what they did here. All right, they replaced, right, and I'm going to just work through it using a pen. So you see this x here, all right, was replaced by 4x minus 7. all right, 4x minus 7, and then plus 7 over here, plus 7 divided by 4. All right, so again here we see minus 7 and plus 7 become a 0, so we are left with 4x divided by 4, 4x divided by 4, and then the 4 and 4 divide, and we are left with x. Okay, 4 and 4. So now that we've seen that f of g of x and g of f of x both give a final result of x, we can conclude that f and g are inverses of each other. F and g are inverse functions. So this is how you're going to verify whether two functions are inverses of each other or not. Okay. Now we'll talk about how to find the inverse of a function. Now there's a step-by-step process, as I said before, and it is over 2 slides, so there are quite a few steps, but if you follow the steps, it's very easy. And I have put up some worksheets also on Canvas, and you can with the steps, all right, some example problems that you can work on, and I have laid out the steps for you to go one by one. However, in the test and exams, those steps will not be provided to you, so you should know the steps. But initially, to practice, I've created some worksheets with the steps laid out, but they are all the same as what we are going to see here in these slides. So let's go through them. It says the equation for the inverse of a function f can be found as follows. First step is to replace f of x with y in the equation for f of x. Then interchange x and y. Number 3, solve for y if this equation does not define y as a function of x. The function f does not have an inverse function, and this procedure ends in step 3. If this equation does define y as a function of x, the function f has an inverse function. And then final step, it says if f has an inverse function, replace y in step 3 by f, so a superscript of -1 of x, and then we can verify our result by plugging in the inverse function into the original function and see if we get a result of x, and then do the converse of that, that is plug in the original function into the inverse function and see if we also come up with x as the resulting value. So those are the steps, but it's important we go through an example and apply these steps to find the inverse. Now in this slide, we have an example to work through to find the inverse of a function. So we have been given a function which is f of x equals 2x plus 7, and the exercise is to find its inverse using the steps that were given to us in the past 2 slides. Okay, so we will go through the steps one by one. So first step was to replace f of x with y. It's a very simple step. Just replace f of x. Remember, f of x and y represent the same thing, right? So I'm going to work through the steps myself, write it down. It might be easier for you to follow. So we start with f of x equals 2x plus 7. So the first step says replace f of x with y. So I'm going to replace f of x, this entire f of x, with y and rewrite the equation, the function. All right, so very straightforward. All you do, there's no mathematics involved here, all you do is replace f of x with y. Then it says interchange x and y. That means make the y, all right, what you got in step 1, just switch, make the y an x and the x a y. So that's what they mean by interchanging x and y. Switch the x and y variables. So I'm going to make y x and then 2y plus 7. So again, this is also a very straightforward step. You are not doing any mathematics here. All you are doing is replacing y with x and x with y. All right, you're not doing any calculation, no algebra involved so far. So in the next step, they said solve for y, and now is where algebra comes in. It says solve for y. So we have to solve for y, which has taken the place of x. All right, so solve for y means y by itself on one side, everything over to the other side, right? So I'm going to rewrite this equation as 2y plus 7 equals x. Now, I'm doing that simply because we are used to seeing uh, the variable, solved variable on the left hand side and the equation on the right hand side, correct? So I will want the y to be on the left hand side and everything over to the right hand side. So all you do is just switch the sides. 2y plus 7 goes on the left hand side and x goes on the right hand side. All right, now that we are solving through it, we are solving for y step by step. First, I'm going to take that plus 7 and bring it over to the next side. So it's going to be 2y equals x minus 7. And at this stage of mathematics, at this course level, you should know that when you're switching, um, taking a term from one side to the other, we have to switch the signs, right? And now we are solving for y. We have to get rid of the 2. So you divide both sides by 2 and we have y equals x minus 7 over 2. And now in the final step, again, all you do is, remember in the beginning we had replaced replaced f of x with y. Now you revert it back, replace the y with f inverse of x notation equals x minus 7. That says that this is an inverse function of the original function 2x plus 7. Here we'll talk about a special test to determine whether a function will have an inverse function or not. And that test is called the horizontal line test. Now, previously, if you recall, in the beginning of this chapter, we talked about something called a vertical line test, right? We talked about a vertical line test, and that test was used to determine if the graph was that of a function or not. So let's say we were given a function f of x equals absolute value of x. All right, this is our function, and we want to determine whether from its graph whether it is that of a function or not. So the graph of the absolute value function is a V-shaped graph looking like this. And what is the vertical line test? It tells us to draw some vertical lines through this graph. Vertical lines, although my lines don't look too vertical, but anyway, we draw a few vertical lines, and then if the vertical lines intersect the graph at just one point, then the graph is that of a function. Then we can conclude that, yes, the graph is that of a function. So the vertical lines have to intersect in only one point in order for a graph to be that of a function. Now, here we will talk about the horizontal line test, which applies to inverse functions. In other words, the horizontal line test will help us determine whether a given graph will have an inverse function or not. So we are going to take the same V-shaped absolute value function graph and perform the horizontal line test on it. All right, so let's go to the horizontal line test. The horizontal line test, and that's used to determine whether the same function will have an inverse or not. So we'll take the same function f of x equals absolute value of x, and we'll draw a V-shaped graph. And now we draw a few horizontal lines through this graph. So let's draw some horizontal lines going left to right. Okay, so draw a few horizontal lines and see whether they intersect at one point or more than one point. So here we clearly see that the horizontal lines intersect at 2 points, right? Each horizontal line intersect at 2 points. So that means this function, this absolute value function as is, the graph will not have an inverse, because in order for a, a graph to have an inverse, the horizontal line should intersect or can intersect at only one point. It cannot intersect at more than one point. Let's go through this example of applying the horizontal line test. So it says here, which of the following graphs represent functions that have inverse functions? So they have two graphs here, a V-shaped absolute value function graph, and then this graph here. All right, we have two graphs given to us. And we draw our horizontal lines, and like we saw previously, this horizontal line intersects the V at 2 points. Therefore, this does not have an inverse. All right. B, on the other hand, all right, this graph here, exponential graph, we draw the horizontal line and we see it intersects at one point. You can draw other horizontal lines through this graph as well, and they will all intersect the graph at exactly one point. So the conclusion is graph B represents a function that has an inverse. Graph A does not represent a function that that has an inverse. All right, and later on we will learn how to restrict the domains of a function in order to get an inverse function for that graph. So even though this V absolute value function graph will not have um, an inverse, but by restricting the domain values of this function, we can get, it is possible to get an inverse of the function using restricted domain values, right? Going into the graphs of f and f inverse. So how would the graphs of the original function and its inverse functions look like? It says here the graph of the inverse of f is a reflection of the graph of f about the line y equals x. In other words, what does this line y equals x look like? All right, so if this is the axis, this is the point of intersection, the x and y axis. So if we draw a straight line through the point of intersection, all right, that is the line of y equals x. And what this says is the graph of the inverse function is a reflection of the graph of f about this line. All right, about this line means if there is a point over here, its reflection across the y equals x line will be somewhere here. All right, it's going to be somewhere here. So that's what graphs of f and inverse of f will look like. We will go through an example in the next slide. Let's look into an example of graphing the inverse function using the information we have been given about the graphs of inverse functions. All right, so it says here, use the graph of f to draw the graph of f inverse. So the graph on the left hand side, the one in red, is the graph of the original function y equals f of x, and we are asked to draw the graph of its inverse. Now, in the previous slide, we were told that the inverse graph will be a reflection. All right, it's a reflection of f of x, of the original graph f of x, across the line y equals x. So what is y equals x? Y equals x is a line that passes through the intersection of the x and y axis. It passes through 0, 0. All right, so if we draw a line through the point of intersection of, so this is the line y equals x, and the inverse graph will be a reflection of this line across this y equals x, the reflection of this graph across the line y equals x. So what was here will be reflected across here. Now, it may be difficult for us to visualize from the graph where the points should be placed. All right, it may not be too accurate to just look at the graph and visualize and draw the reflection across the y equals x line. So what I would suggest is to find the coordinates of these points. All right, find the coordinates of these points, and then use another piece of information that we learned a few slides back about the domain and ranges of inverse functions. All right, because if we can get the coordinate values of the inverse function, then we can it'll be much easier to locate those points and draw a more accurate graph. All right, so what had we studied a few sections back about the domain and range was that, and I'm going to write here, let's say we have f of x, and then we also have its inverse function. All right, and then we have a domain and range for each of these. Okay, so domain and range. So what we learned was, or what we were told was, that the domain of the original function will become the range value of the inverse function, and the range value of the original function will become the domain value of the inverse function. So basically, the domain and the range, they, all right, sorry, okay, the domain and the range, they switch. Okay, they switch. So what was the domain of the original function becomes the range of the inverse function. The range of the original function becomes the domain value of the inverse function. So if we can find the coordinates of these 3 points in the original graph, then we can switch the x and y coordinates, which will be the coordinates of the inverse function. which is essentially the reflection across the y equals x line. So let's go through that exercise of, all right, of identifying that, of identifying the coordinates first. So we have f of x. So there are 3 points, and then I'm going to write f inverse of x. All right. So let's look at this point here first. This point here. So what are the coordinates of that? All right. It's -2. The x value is -2. And the y value is +2. So that means the coordinates of this point here is -2, 2. So that point has, and let me use the correct, excuse me. Okay, so -2, 2. What about the next one? Okay, I'm looking at this point at the bottom in the third quadrant here. All right, this point here has coordinates -3 for x and -2 for y. So that's going to be -3, -2. And finally, this point here in the first quadrant is 4, 1. +4, +1. So let's write that. It's 4, 1. So now what I'm going to do is to get the coordinates of those same points across the y equals x line, which will be the points on the inverse function graph. I'll just switch the x and the y values for each point. All right. Okay, I'm going to switch. So this 2 is going to be, the +2 is going to be the x value of the inverse graph, and -2 is going to be the y value of the inverse point. So just flip your x and y values of the original function and use that for the inverse function. So what was -2, 2 in the inverse function, it's 2, -2. Then for the next point, it's -2, -3, right? And then we have 1, 4 for the last point here. So as you can see, we switched the x and the y coordinates. What was the domain? The x value in the original function becomes the y value of the inverse function, and what was the y value, the range value of the original function, becomes the domain, the x value of the inverse function. And now we can just plot those points and we'll get the graph of the inverse function. So let's see if that's what's happening. All right, so let's look at 2, -2. So 2, -2 is here, right? 2, -2. All right, so this point here is 2, -2. Then -2, -3. So -2, -3 is right here, and 1, 4, 1, 4 is here. All right, and just connect the points and you get the inverse function graph of y equals f of x. So this point, this blue point here in the fourth quadrant, is a reflection of this point. All right, this point here, okay, in the third quadrant, is the reflection of this line, or this point, okay, across the y equals x line. and 1, 4 is a reflection. This line point here is a reflection of this point across the y equals x line. Okay. This slide just shows what we discussed in the previous slide, that each of the points on the blue graph, which is the graph of the inverse function, is a reflection of the red points, all right, across the y equals x line. So we verify our solution by observing the reflection of the graph about the y equals x line.